about the transformations of functions, right? And we had asked you guys to work on, what, worksheets 1 and 2? That sound right? We'll start with questions from those, and then we'll kind of pick up where we left off. Joe?
Could you go to worksheet 1, just so I can look at problems? I really don't want to get my tablet out. That's cool. Okay. Oh, yeah, perfect. Can we do number 3, please?
Sure. Yep. Yes. Yes. Okay, number 3. So the first thing I want to do is I want to identify the values for AC, H, and K. So I'm going to be comparing to my general form. That looks like this. So the place that I need to be careful about is this piece doesn't look like that. So I'm going to factor that -2 out. So from there, I can identify my A, which is 1, since there's no coefficient out front. My C, which 1 over C is -2, so C has to be 1 over -2. H should be 2, and then K should be -1. Once I have that, I can now describe my transformations using the criteria from page 1. Since C is negative, I'm going to have a reflection across the y-axis. And since the absolute value of C is less than 1, we have a horizontal shrink by 1/2. Since the A is 1, there's no reflection or stretch or shrink. Since the H is positive, we're going to be going right that many units. And because the K is negative, we're going to be going down that many units. And that's all she wrote for that. Other questions from these first two? Rochelle? Okay. So same idea. We'll start by taking care of the inside. So there I will factor a 2 out. So the A is -2. The C is 1/2. The H is 1, and the K is 4. Good with all those? Okay. Since the C is positive, I don't have to worry about a reflection, but the absolute value of C is less than 1, so we still have that horizontal shrink. Since the A is negative, we have a reflection on the x-axis. Since the absolute value of A is bigger than 1, we have a vertical stretch by a factor of 2. Since the H is positive, we're going to be going right that many units. And since the K is positive, we're going to be going up that many units. And that's all. Is that okay, Rochelle? And again, the criteria here was on page 1 of worksheet 1, if you had forgotten those. We went over it in the notes also, but I went and typed it all in there for you too, just so it's in more than one place for you. Joe?
Can we do one of the graph ones, please?
Sure. Which one do you want to do?
Well, it's up to you. Which one do you think was like kind of tricky? None.
None of them?
Okay.
Good. There, none of them for me.
All right, let's do number 7.
Okay.
Number 7.
Okay. So we'll start the same way. I'm going to identify the values for A, C, H, and K. So I'd start by factoring the inside part. So I have that A is 1, C is -0.5, H is 2, K is -1. We okay with those? Okay. From there, I'm going to make my transformation map. So this was something we mentioned in the notes. So filling in my values for C, Y, or CH, A, and K, I have -1/2 x plus 2, and then 1y minus 1. And then what I'm going to do that on are those key points that I gave to you guys. And there was 4 of them. So what I'm doing now is I'm going to take this x and plug it in for x, and then this y and plug it in for y, and that'll get me my new points. So -1/2 times -2 is +1, plus 2 is 3. 1 times 4 is 4, and then 4 minus 1 is 3. And then I'm just going to go ahead and grind these through. I'm not going to say it out loud. I'm just going to write down the answers. Is that okay, Joe?
Yeah, sounds good.
Okay. Oops. And now it's just time to plot. So let's see, I have 3, 3, 2.5, and 0, 2 and -1, 1.5 and 0, oops, and then 1, 3.
Isn't it always supposed to be a parabola?
Yeah, because your parent function was x squared.
Okay.
So it's going to just look like different parabolas.
Okay, right. Cool. And may I go to the restroom real quick?
Sure.
Thank you.
Yep. Last call on questions from the homework. Rochelle? Sure. So we'll start the same way. So I'm going to factor. Oh, number 2, you said. So back here. Okay. So if I look on the inside, there the leading coefficient's already 1, so there's nothing to worry about. So I can go straight to A is -2, C is 1, H is 1, and K is 4.
I get the rest. I just like to know how like the ones work.
Oh, sure. Yeah. So this is like 1x, so that's where the C is 1 comes from. Cool. Okay. Let's move this show on the road then. We're going to start chapter 3 today, and we're going to start section 3.1. So today we're going to be talking about graphs of sine and cosine functions. So from last time, we saw that if we have some parent function, we can describe any transformation of that parent function in the following way, where the A, C, H, and K control the different types of transformations. So that was like our algebraic way of taking a parent function and transforming it. And then we saw also that if we had a point from a parent function, we can transform it into a point in our transformed function using this map. So this is like our geometric or graphical kind of way we can do a transformation. We're going to be building on these two ideas today, talking specifically about sine and cosine functions. So we're going to come back to these ideas throughout this first lesson, okay? But I just wanted to make sure that we had these down so that when we refer back to them, they're still there. We're going to start, though, with like a bit of an information dump. So I'm going to build myself a table. My table is going to have like, what's it got? 4 columns and a whole bunch of rows, like maybe 10 rows or something is what this table is going to build that, or going to have that I'm building. So I'm going to start just with this first column, which is just a bunch of labels. And there we go. Some of these labels are things that we recognize from chapter 1. And some of these labels are things that are new that will describe what it is that we're talking about here in a moment. Okay, so there's the guts of my table here. We're going to talk about 3 different kinds of functions. So we're going to talk about the sine function, the cosine function, and then any transformation of either the sine function or the cosine function. Okay. So we're going to now work on filling in the rest of this table and kind of talking about how we go about doing this. This isn't something that I would expect you to repeat on your own, but I think it helps us remember some of the things on this table if we kind of explain where they're coming from. You know what I mean? So rather than just being like, copy this down, we'll kind of talk about kind of how we go about getting this information that I'm going to fill the table up with. Okay. So let's go back and think about chapter 1. When we talk about a domain, that's the set of inputs for our function, right? Everybody's okay with that? For sine or cosine, the inputs are angle measures. Everybody's okay with that? You do like sine of 30 degrees or sine of pi over 12 or whatever, you know, right? It's an angle measure. In the last chapter, one of our big accomplishments was we moved our definition of sine and cosine out of being based on right triangles and moved it on to being based on points on the unit circle, right? So to do that, we defined like a standard position angle where one side is on the positive x-axis and then the terminal side like rotates around. So what that did is it allowed us to describe angles of any size, right? The angles can be negative valued, positive values, as big as you want, as small as you want. We can always draw an angle for it. Everybody's good with that? And then we built out our definitions of sine and cosine to where sine and cosine correspond to points on the unit circle. So if I want to find sine of 146 degrees, I draw my standard position angle at 146 degrees and look at where that terminal side intersects the unit circle. Everybody's okay with that? Now, any angle I draw is going to intersect the unit circle. Everybody's okay with that idea? Or the terminal side will intersect the unit circle, right? And because I can draw any angle I want, that tells me then I can take the sine or cosine of any angle. So that tells me that the domain is going to be all real numbers. So we can take sine or cosine of any angle. And because we can represent any number as an angle, that's how we get all real numbers. So I'll use the interval notation to describe that. And that's true for both sine and cosine. That. Drop it over here. So let's talk about the range now for sine. The range are going to be the outputs, right? So for sine, those outputs are going to be the y-coordinates of the points on the unit circle. So for example, if I'm talking about the sine of 90 degrees, 90 degrees is my input. The output would be the y-coordinate from the unit circle, which is 1. Everybody's okay with that idea? Okay. So if I look at my set of outputs then, the outputs that sine can have are the same as the y-coordinates from the unit circle. Well, the smallest y-coordinate on the unit circle is -1. The biggest y-coordinate on the unit circle is +1. And all of the y's in between are covered, right? Because the unit circle is connected between those 2 points. So any y-coordinate you want to choose in between -1 and +1, there's a point on the unit circle that has that y-coordinate. Everybody's okay with that idea? So what that means then is the range for sine is going to go from -1 to +1. Notice that I'm using brackets here because sine can have the value of -1 and +1. Those outputs are available, so that since they're included as possible outputs, I use the bracket as opposed to the parenthesis. Everybody's okay with that idea? For cosine, the outputs are the x-coordinates. The smallest x-coordinate is -1, the biggest x-coordinate is +1, and all the x-coordinates in between are used because the circle is connected in between those 2 points. So the range for cosine is exactly the same. Oops. Again, notice the brackets as opposed to the parenthesis. So far, so good? let's now take a look at the graph for sine x, and we'll talk about how I would go about getting this graph. Okay. So this is the graph for sine. So this looks kind of weird. And you might ask, Mr. Kulik, how'd you go about generating a graph like this? And I would just say, I'm just going to use the unit circle. Remember, the unit circle is giving us the inputs and outputs for sine, and also the inputs and outputs for cosine. So for example, let's say this first. Typically, when we're graphing sine or cosine functions, we use the angle measures in radians, and that's just from a practicality standpoint. If I want to graph one full go around the unit circle, it's a lot less tick marks to put on my graph to have the x-axis go from 0 to 6, which is a little bit less than 2 pi, versus going 0 to 360. 360 is a lot of tick marks to put on my x-axis. So typically when we're graphing, we're going to use radian measures. So for example, one point that I would plot could be 0 as for 0 radians, which gives us the output of 0 for sine. So I'd plot the point 0, 0. So basically all the points here are going to be an angle measure, and then the value for sine of that angle. So maybe next one I did pi over 2 and 1. That's here. And then pi and 0. So that'd be like here. 3 pi over 2 and -1 is like here. And then 2 pi and 0 puts us back to here. And I can fill in any more points from the unit circle I want and keep going around the unit circle. But that's basically all we're doing. That's how we kind of get this graph, is we're just using points that we generate from the unit circle. Any points are fine. I just jumped around to pick those specific points because they're easy to find, because they're the maxes and mins and x-intercepts. So they're just easy for me to find on the graph. But that's all I'm doing to generate that graph. I would not ask you to do that on your own. We'll talk about how we'll actually go about graphing things here shortly. But generating those values for the actual sine or cosine function, I would not ask you to do by yourself. Okay, so this is what the graph of sine looks like. The next thing we're going to look at is the symmetries. So if you think back to chapter 1, there's 3 types of symmetry we described. Notice here that the picture, if I look at one quadrant and the other quadrant, they look like they're kind of reflections of each other if you kind of go across that diagonal. That was a certain type of symmetry, was indicative of that type of graph. That was called odd symmetry. So sine is odd. So let me do this real quick. So I'm going to drop in that graph of sine because there things are in radians. I put the x-axis in radians for us. It's the same graph, though. I could do the same thing, kind of generating my graph for cosine. So this is what the graph of cosine looks like. Notice that it's quite similar, but it's not exactly the same, right? Again, the reason that we're doing that, or the reason we're getting something different, is if I go ahead and graph cosine, so I'd have 0, 1, pi over 2, 0, pi negative 1, 3 pi over 2, 0, and then 2 pi and 1 again. And then I could keep going if I wanted to, but would generate the graph the same way. If I look at the graph of this, notice that quadrants 1 and 2 are like a reflection of each other. That was indicative of a type of symmetry. That type of symmetry was called even. When I look at those graphs that I drew of sine or cosine, next thing we're talking about is continuity. If we think back to chapter 1, we talked about discontinuity, right? We talked about asymptotes and jump discontinuities and removal discontinuities. Do you see any of those in our graphs? No, right? No, there's no vertical asymptotes, there's no jumps, there's no open circles. So what that tells me then is just that these two functions are continuous everywhere. Yes.
So do we always have continuity? Continuity. Do we always have that on these type of graphs?
Yes.
Because like you can't really have any of the things that you listed, right?
Correct. Now some of the other ones, the tangent, cotangent, etc., you might not.
But for sine
and cosine have continuous everywhere.
Okay.
Yep. Okay. Next up are these four that maybe are unfamiliar sounding words. We're actually going to talk about the midline first. So let's talk about what we mean by the midline. So the midline is basically a horizontal line that's going to divide the graph into like two even pieces. So for the case of sine, that midline is here at the x-axis, or y equals 0. We see that if we think about the area between the midline and the curve, there's as much area above the midline as there is below the midline. That's kind of what we mean by splitting it into equal. Is that okay with everybody? Okay. If we did the same thing with cosine, notice the midline would be in the same location, right? So I'm going to put next to y equals 0, I'm just going to write the x-axis. Okay. Everybody's cool with what we mean by midline? Pretty obvious, right? Visually, all you really need to do is be able to look at it visually and be able to pick one out. The next thing we'll talk about is the amplitude. So you can think about the amplitude as the distance from an extreme point, like a maximum or minimum, back to the midline. Or, if you wanted to, you can think about it as half the distance from a max to a min. Yes, of course. Either way of thinking about it is fine. I usually think about it as an extreme point to the midline, but on occasion it's useful to think about it the other way. So in the case of sine and cosine, that amplitude's just going to be 1, right? If you look at the distance here from the midline, which is at 0, up to the maximum, which is at 1, so it's 1. Let's go back to the graph here. The next thing we're going to talk about is the period. Notice how this graph kind of repeats itself over and over and over again, where we have if I start here, I have like an up hump and then I go and do one of these down humps, and then it starts over again. We actually change colors at that point. We start a new up hump and down hump. Graphs that repeat themselves like that are called periodic graphs. And the length of one of these non-repeating sections is called a period. And I should say it's the horizontal length. So for example, that purple section is 1 period. So the period length, we're starting at negative 2 pi and we're going to 0. So the length for that is just 2 pi. Everybody's okay with that idea? The same thing holds for cosine. So they're both have the same period, which is coincidentally 1 trip around the unit circle, right? If you think about us, how we generated the points, you do 1 trip around the unit circle, and then you start repeating the same thing that you did the next time through. Oh, sure, of course. Like, that makes a lot of sense. The last thing we have to add to our table is for these 2 columns anyways, is the frequency. The frequency is defined as the number of periods per 1 unit length. So by that definition, the frequency is always going to just be the reciprocal of the period. So in our case of sine and cosine, that's just 1 over 2 pi.
You said it's the reciprocal of the period?
Yes. Yeah.
And we always have a period then for sine and cosine.
Yes.
It's like equal parts or whatever.
Yeah, because they're just repeating sections
Right.
over and over and over again. That's what the graph looks like. Goes on forever in both directions,
Yeah.
just repeating it, whatever it's been doing.
Okay.
Okay, so let's talk about then these transformations, right? So remember that we had 3 different types of transformations. We have stretches and shrinks, either vertical or horizontal. Those are broadly called dilations. We have reflections across either the x-axis or the y-axis. And then we have translations, either up or down or left and right. Everybody's okay with that? Okay, so the domain was all real numbers. If I stretch something out, or I reflect it, or I pick it up and I move it, can any of those actions like create a vertical asymptote, or tear a hole in the graph, or like rip 2 pieces apart? No, right? Geometrically speaking, we know that none of those things, the graph is going to basically still look the same. It'll just be like stretched out or flipped over or moved to a new location, but you can't like tear a piece off of it or something, right? So because it's going to stay connected and ostensibly be basically the same picture, can the domain change? No. If it had to cover all the x values before, and all we can do is kind of like stretch it out and move it around, it's still going to cover all the x values. So the easiest question we could ever ask you is the domain for one of these sine or cosine function, because it's always all real numbers. It doesn't matter what else you're doing to it. And the continuity then, obviously, if it didn't have any holes in it before, and you can't rip any holes in it with our transformation, still can't have any holes in it. Yes, of course. Okay, let's talk about the range now. The range is associated with the y-coordinates. Can the y-coordinates change with one of these transformations?
No. No. Wait, yes.
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 What type of transformation can change the y-coordinates?
Yeah.
Okay, a vertical shift, right? If I have the graph here, I pick it up and move it, the y-coordinates are all going to be different, right? Okay. Is there another one that will also change it?
Vertical stretch or shrink.
A vertical stretch or shrink, right? If I had it before, was here, and I stretched it out, the y-coordinates got bigger that way also. Everybody's cool with that idea? Okay, so what coefficient A, C, H, or K controls the stretch or the vertical stretch and shrink?
H, right?
The A.
Okay.
And then which one controls the shift up and down? The K. If I go back and I remember, and I look at my map here, I know that the A coefficient is multiplicative, and the K coefficient is additive, right? So my old range was -1 to +1. When I multiply that by A and add K to it, I'll write that, it would have like -A plus K. I'm going to write it as K minus the absolute value of A. I'm just putting the absolute values around A because A can be positive or negative. But really, we just want to make sure that when we write our interval, the smaller number is first. So we want to make sure that we're always talking about like the positive version of A. And we do the same thing to the 1. We'd have A or absolute value of A plus K. Or again, I'm just going to write it in that order, just so it's for consistency's sake. Is everybody okay with that? So you took your old y coordinates, you multiply them by A, and then you add K to them, and you get your new coordinates. You do that to every single coordinate. Whatever was the minimum before has now been multiplied by A and added K to it. And the maximum from before was multiplied by A and added K to it. Is that okay with everybody?
So cool. It's going to be a really dumb question.
No, it's
But,
okay.
Okay, what's our A value in this case? Is it just 1?
So here, yeah, so A is 1, C is 1, H is 0, and K is 0 in like the parent function versions. Over here, we haven't specified what
so-
A and K and H and C. They could be any numbers.
So it's just like a general statement?
Yes,
Just whatever.
we're developing like a formula
Right, okay.
that we can take something, and now we don't have to even look at the graph to come up with the domain and range.
Right.
We can just apply this formula.
Okay, cool.
The symmetry we're not going to worry about because oftentimes the transformation can just destroy the symmetry altogether. So certain values of H will just undo any symmetry that you might have had, so we're not even going to worry about it. It's difficult to predict. The amplitude, that was the distance from the midline to a maximum or minimum. Can that change with a transformation?
Yes.
Yes. Okay. What transformation will change that?
A vertical.
A vertical stretch or shrink, right? If it pulls it taller, the midline stays in the middle, but the extreme points have gotten further away, or if it's compressed, it'll get closer together. So again, remember the A was multiplicative. That controlled the stretch or the shrink vertically. And since the amplitude is a distance and the A can be positive or negative, we're going to think about it as absolute value A. So just did A times 1, gave me A. But remember, A can be positive or negative, but the amplitude's a distance, so we just absolute value it to make sure that it's a positive number. Okay. Can the midline change with the transformation? Can. So let's say that our graph is here. The midline's right through the middle. What if I picked it up and moved it up here?
Oh, okay, yeah. Yeah, you're right. Yeah, okay.
Okay. So a vertical shift will change the midline. Everybody cool with that? And the vertical shift was controlled by A, C, H, or K.
Vertical is A. No, yeah, it's A.
The shift up and down vertically, though, is K.
It's K. Stretch and shrink.
And yes. And remember that K is additive. So my old equation was y equals 0. When I add K to that, I just get y equals K. Can you grab the door for me real quick? It just, lunch is getting out or whatever, and it's getting a little noisy. Thank you. Everybody's happy there? Period. Can that change with the transformation? So that's like the length of the repeating units, right?
Probably.
Okay, it can. What type of transformation will change that period? It's like the horizontal distance of one of those repeating sections. Yeah, it's the horizontal stretch or shrink, right? If you pull something wider, that period now has gotten wider. Or if you squish it together, it'll have gotten shorter. Very good. And remember, if we go back and we look, the C is multiplicative. So because the period was 2 pi before, it'll then be 2 pi times C. But C can be positive or negative. So we'll just stick, and a period is a length, so we just stick an absolute value around the C and we're okay then. Everybody's okay with that? And the frequency is just the reciprocal of the period, so that's easy. It's just going to be 1 over 2 pi C. So far, so good. Let's look at an example here where we apply this. To get him? It's been like a little fruit fly or something buzzing around me all day.
Did you get it?
I don't know. I don't have a carcass on my hand, which makes me think I probably didn't. Maybe I just scared him away. Anyways, so let's say we have the parent function is y equals sine x. And let's say our transformed function is y equals negative 2/3 sine of 2x minus 4 plus 1. And let's say we want to find like the domain and the range and the amplitude and the midline and the period and the frequency and all that jazz. Okay? First thing I'd want to do is identify the values for A, C, H, and K. So that means having to worry about factoring this inside piece. Everybody's okay with that? Okay, so what's the value for A going to be? We're looking at the transform function.
Oh. Is it negative 2/3?
Yes. And the value for C, it's going to be?
Is that 1 over 2?
Okay, very good. The reciprocal of 2, so 1 over 2. And the value for H is going to be?
2.
2. It's going to be?
It's the same sign.
Yes. So positive 2. And then the K should be? Very good. Okay. So if I want the domain then, what's that going to be? It's the easiest question.
It's the negative infinity and positive.
Yeah, it's still all real numbers, right? That part never changes. And then what's the range going to be?
Same thing, right?
Nope.
Change it a little bit.
Remember, that goes from K minus the absolute value of A to K plus the absolute value of A. So in our case, the K is 1, and the absolute value of A is 2/3. So that's going to be going from 1/3 to 5/3. We okay there? What's the amplitude going to be?
What's the amplitude again? Is that the value of 1?
So the amplitude, we're looking at the transformation column though.
So it'd be negative 2/3.
Well, it's the absolute value of A.
So 2/3.
So the absolute value of 2/3 or negative 2/3 is positive 2/3. Okay. What's the midline?
Scroll up.
Sure.
Okay, so 1.
Okay. Very good. So it says was y equals k. So we'd write y equals 1. Got to make sure you put the y equals there. The midline is a line, so it needs to be written as the equation for a line. Just writing the number 1, I will not give you full credit for that. It needs to be written as an equation. Are we clear on that? Okay. What's the period? Yeah, so it's 2 pi times the absolute value of c. And then RC is 1/2. So that just comes out to be 1 pi. Is everybody okay there? And the frequency is always just the reciprocal of the period. So 1/pi. Happy with that stuff?
Bueno.
Again, all I'm really doing is using the information from the table to kind of compute these things, right? Okay. Let's talk about now actually doing the graphing piece. So what we'll be using to do this is this transformation map that we discussed last time. The question for us is going to be, what points should we be using? I'm going to just give them to you right now. So for sine, those points are the following. Now I have these memorized because I'm an ancient mathematics teacher that's done problems like this like literally thousands of times in my life. So I've memorized these points because I've used them like thousands of times. I would not expect you guys to do the same. So this would be information that I would provide for you. You do not need to memorize these points, but you should put them somewhere in your notebook where they're easy to find because you will refer to them not infrequently. And once we finish doing all of these, I'll type them all up and put them into a single document for you. But that's something that you'd want to highlight in your notes because we'll refer back to this to do several things. So these are like your key points that you'll use for graphing. So I have a set of points for sine, a set of points for cosines. Okay with that?
Let's give you the content.
Yep, it's all in the content library also. Here, I'll do this, make it easier to find. Right?
You said this is going to be provided on a test?
Yeah, not something I'd expect you to memorize.
Well, we should memorize the, what's it called? The reflections.
Yeah, you'd probably want to have that part. Yeah. Again, should be fairly familiar. It was the same criteria from last year, really.
No problem.
Okay, so let's do an example. Let's say that we want to graph y equals negative 2 sine of 2x plus pi over 2 minus 1. And this is similar to something that I would ask for you guys to do on the on your worksheet, so I want to pull the same grid that I would use. So let me do that real quick to put this in so it looks the same. Actually, gosh darn it. So, first things first, I want to identify my values for A, C, H, and K. So I'm going to, again, worry about factoring the inside here. So I'm going to factor off a 2. 2x divided by 2 is just x. And then pi over 2 divided by 2 is the same thing as pi over 2 times 1/2. Which would be pi over 4. Notice that when I distribute the 2 back through, it reduces down the correct way. So now I can identify my values for A, C, H, and K. I'm going to use those values to write my transformation map. So I'm just going to fill in. So C is 1/2. H is negative pi over 4. A is negative 2. And K is negative 1. Everybody okay how I filled that in? And now I'm going to just use my key points that I listed before. There are 5 of them. And what I'm going to do to get my next point is I'm going to take my x value, plug it into x, and then take my y value and plug it in for y. That's going to be negative pi over 4, and then negative 1. Is everybody okay with what I did there? So I'm just going to go ahead and just write down the answers. Are we all okay with that? Okay. If we need to go back and like fill in a blank here or there, I'm okay doing that, but it should be relatively straightforward. Just some fraction arithmetic in my head. You know what I mean, guys? And again, I showed you how to do the fractions with the pi on your calculator, right? You just leave the pi out and do the fractions and use the fraction button, and it'll spit out the final for you. Everybody feel okay about what we did there? Okay, let's go ahead and graph this now. So if I look at my grid, the x-axis is labeled in terms of pi, so every one of these grid lines is like half a pi. Everybody's good with that? So a quarter pi would be like half of a half, right? Notice that I'm going by quarters. So negative a quarter and negative 1 would be there. 0, negative 3 would be down there. A quarter and negative pi and negative 1 would be there. A half a pi and positive 1 would be up there. Now this is Okay. So I don't know what happened here on this, but this is supposed to be a -2 is supposed to be down here. So that should be -1's there. Oh, all right, hold on. I lied. This should be 2 and this should be 4. Okay, my apologies. I don't know. You ever make a mistake? Happened to me. And then a quarter and -1. And then we have a half and +1. And then 3/4 and -1 back to here. Everybody's okay with that? So that's one period. Now, I'm going to ask on problems like this that you continue to repeat that pattern and fill all the space provided. So I'm not going to ask you to generate any more points manually. I'm just going to ask you to like put the point in the right spot and then draw the rest of the graph. So if I start here, from there I should be going down to the minimum and then back to the middle and then up to the top and then back to the middle, down to the bottom, back to the middle, up to the top, middle, bottom, middle, top, middle, bottom. And then I should do the same thing over on this end here. So we're at the middle. We had just gone down to the bottom, so we should be coming there from a top. Is that okay with you guys? Again, all I did was just repeat the pattern there. On your papers or on your test, I would expect to see like, you see how it's obvious where my points are? I'd expect to see the points there and not just like a doodly 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 doo. Just so I can make sure you don't have to be like, you know, the neatest thing in the entire world, but you got to be pretty close. Have the points in pretty much the right spot. Is that okay? And then if your graph is a little shaky like mine is, looks like I have Parkinson's disease or something while I'm trying to write this and my hand's going all over the place. I won't be, you know, it makes it easier for me to grade what's going on. You know what I mean? But all the problems now are ostensibly like this, right? If it's a cosine function, there's different key points, but you're doing everything exactly the same. You find your A, C, H, and K the same way. You build the same map. You have different points that you transform, but like whatever, it just like the arithmetic is a little different, and you do the same thing. You plot and extend if you have to, the same way. So nothing really changes. One problem is about the same as any other problem, right? We okay with that idea? Good. Okay. Let me check one thing real quick. I can't remember. I think this is where we stopped. I just want to make sure. Yes. Okay. I just didn't want to get to a different spot in the two classes. So this is where we'll stop here for today. Does anybody have any questions about this before we move forward? Okay. So this means that you guys should be able to do now worksheet 3. So the beginning part of worksheet 3, we're asking you to find these like amplitude, midline, period, frequency, and then do the transformations again like you did on the previous sheet. And then do some of these graphing problems. I have a couple of them set up here for you. Sound okay to that? On your asynchronous day, Thursday, I've made up a short little lesson for you guys already. The video's already on My Notre Dame. It's like 15 minutes or something, so it's not a lot. But it should be enough for you guys to work on worksheet 5. So in the video, you're going to talk about how you can go from a graph back to an equation. And worksheet 5 really just has a couple of different, has like 2 problems on it, basically, for you guys to work on. Leo?
Does that mean we also have to do worksheet 4, or are we skipping 4?
We're skipping 4 for now. We'll get to it, but I think it's more difficult than the worksheet 5 topic. So if I was going to pick something to do by yourself with just a limited video, the worksheet 5 seemed like the better option because they could be really done in either order. So that was my rationale there. We would be doing them both on the same day if we had like in class, but I think that would be too much to ask for you guys to do by yourself. So to wrap up here, the homework check for Sunday is going to be just worksheets 1 and 2, the stuff that we've done and we're able to ask some questions about. The next homework check on the 17th, you'll have this worksheet 3 and 5, and then potentially some more stuff from next week. And that's all reflected on My Notre Dame. If you go and you look, you'll see that there's already the assignments for next week and this week are all kind of set up already. Is everybody clear on what's going to happen on your asynchronous day and what's due this Sunday's homework check? Okay. Well, I'm going to